Alright, so in this video we'll talk about the equation of a line. We know from previous videos that, and by solving a problem, that if you're given 2 points, a unique line passes through it, A, and B, if you choose a random point that lies on the line, say a point P of the coordinates x, y, a very general form of a coordinate, we were able to show that if this point lies on the line that's formed by 2 points A and B, that the coordinates of the point satisfy a given equation. And that equation turns out to be the equation of the line. Using those similar ideas, what we can do is we can define what an equation of a line is. And the formal definition goes as follows. The equation of a line or a curve is a rule for determining whether or not the points with coordinates x, y, which was P in our case, lies on the line. So if we were given the line y equals 3x minus 9, which was the case in our previous example, we showed that the point 3, 0 lies on the point, is present on the point, and we also showed many other points which are also present on the line. But let us check whether the point 5, 1 is present on the point or not. So for 5, 1, what we can do is we can substitute 5 and 1 for x and y respectively and check whether this equation is satisfied. So x turns out to be 5 and y turns out to be 1. So the LHS on the left hand side of the equation becomes, well, quite simply 1. And the RHS becomes 3 times 5 minus 9, which is 15 minus 9, or, well, 6. So as we get LHS is not equal to RHS, well, we can safely say that this point does not satisfy this equation and hence does not lie on the line. So our point 5, 1 should lie somewhere here, but not on the line. It should lie away from the line because it does not satisfy this equation. Whereas our point 3, 0 should lie on the line, and I can't draw it here because 3, 0 lies on the x-axis as a y component is 0, and if you can imagine that the line extends in the reverse direction, the reverse x-axis, it should intersect with the x-axis at a particular point, and that point should be 3, 0. Again, don't go by the diagram in this case because the diagram is not representing the right line, but conceptually it all makes sense. Let us talk about this point, which has a form, well, 0, c, where c is just the height. I choose this height to be represented by the variable c, and the point lies on the y-axis as well as on the line. Let us see if 0, c satisfies this equation, and let us try to find the value of c. If this point lies on the line, we can substitute it there, and RHS turns out to be c. Oh, sorry, the LHS turns out to be the c, which is just the y component of the point, and the RHS turns out to be 3 times 0 minus 9, or minus 9. So, since RHS equals LHS, why? Because the point lies on the line, we must have c equal to negative 9. Or, this point, in fact, should be equal to 0, negative 9. So, we have shown that 0, negative 9 lies on the line because it satisfies this relation, or the equation of the line. 3, 0 satisfies this equation, hence lies on the line, whereas 5, 1 does not satisfy this relation, and hence we can say that it does not lie on the line. So with that description of what an equation is, from where we started originally, from the definition, we said that if an equation is given to us, and we substitute the x and the y values of a particular point, and we find the equation to be satisfied, we can very well claim that the point lies on the line. And if the point does not satisfy the equation by substituting in the x and the y components of the point, we can say that the point does not lie on the line. And that is basically what an equation means conceptually. Now, with that information, let us solve for very general examples. The equation of a line. So let me draw a line here. Let me choose another color. Yeah, yellow works fine. Let this be our line for the moment. And let us have 2 points through which the line passes. Let that be x1, y1. And the second point be x2, y2. Solving for a general point as we did in our example before, say a point P, which rests here, of the coordinates x, y, we can do, like again as we did in the example, what we can do is we can satisfy the slopes of this and equate it to the slope of this, and also equated to the slope of this, because as it's a line, the slope at every point x, y on the line should be the same. Doing that, we realize that, well, the slope, this is slope 1, let us call this slope 2, let us call this slope 3. Slope 1 turns out to be y minus y1 divided by x minus x1, and that should be equal to slope 2, which could be y minus y2 upon x minus x2, and that should be equal to slope 3, and that turns out to be y2 minus y1 upon x2 minus x1. More generally though, we usually call the slope to be equal to a value m, because if we know what the line is, we usually know in which direction it's heading, or we know how steep the line is. And if we know that, we know the gradient. And we usually call it by a variable m. So we have this term equal to m, and we have this term also equal to this, which is a function of x and y, and as well as this, which is also a function of x and y. We can take any combination of this, and for example, let me consider y minus y1 upon x minus x1 equal to the slope of the line, which is m. In that case, the equation of the line becomes y minus y1 equals x minus x1 times the slope. And this is what we refer to as the equation of the line. We could have also checked the form using this, and that should have given us y minus y2 equals m times x minus x2. Now, let us check if one of the points satisfies the equation. So, as we know from our previous discussion, that if a point satisfies the equation, that means the LHS equals to the RHS, then that point lies on the line. So, let us take this equation, and let us see if x1, y1 lies on the line. So again, doing the same thing as what we did before, the LHS turns out to be y1, this is what we substituted here, minus y1, which is already present here, and that gives us 0. And the RHS turns out to be some slope multiplied by x1 minus x1, which is also 0. So since LHS equals RHS, well, the slope turns out to be, the equation is satisfied, and hence the point lies on the line, which is initially what we started with. So this is a good direction that we're heading into. If you do the same thing for the point y2, x2, y2, let's just try to satisfy this equation. We should hope that LHS equals RHS, because y2, x2 also lies on the line. And let us do that now. So our equation would be, if we work with this equation, from this equation it's very easy to see. If we put y equal to y2, this turns out to be 0, and this turns out to be 0. LHS is also equal to the RHS here, and hence the equation is satisfied. But let us check if x2, y2 satisfies this equation, which took into account the coordinates of the first point, not the second point, for which we're testing. So we would have the LHS to be y2 minus y1, and the RHS to be m times x2 minus x1. Well, at this point, it doesn't seem to satisfy because these two terms are not the same. But if you dig a bit deeper, we realize that m is nothing but y2 minus y1 upon x2 minus x1. We can substitute that value of m to get y2 minus y1 upon x2 minus x1 multiplied by what we had here, x2 minus x1. We can very well at this point cancel out the terms x2 minus x1 from the denominator and the numerator. What we end up getting is y2 minus y1, which is the LHS. So for point x2, y2, we've also shown that the RHS equals the LHS, which is a good thing. So from any two forms of the equation, this or this, we have shown that x2, y2 and x1, y1 lies on the so-called equation of the line. And that is what the description of the equation of a line is.